Swayam Prabha. Digital India. Educated India.
So, today we will continue our discussion on modeling of distillation column. Modeling of distillation column. So, in the last class we have derived mass balance equations. I mean, first we have derived total mass balance equation along with the component mass balance equation. Fine. Now, we have mentioned that the total mass balance equation is used to calculate liquid hold up represented by M. Unit is suppose mole, and component mass balance equation we can use to calculate liquid composition, which we have represented by X, and X is the mole fraction. Fine. And based on some assumptions, we have concluded that all vapor flow rates are identical. That means V1 equals to V2 equals to Vn equals to Vb. Now, other variables, I mean apart from these variables, include the vapor phase composition. Fine. Another one is liquid flow rate. We have discussed the calculation procedure of vapor flow rate of any component I, that is yi equals to alpha ij xi divided by 1 plus alpha ij minus 1 into xi. This equation we have derived, and this is called as equilibrium relationship. Equilibrium relationship. Our assumption is that alpha ij remains constant throughout the column. So, alpha ij is known, x we can get from the component mole balance equation or component mass balance equation. So, we can calculate the vapor composition. Today we will discuss the calculation of this liquid flow rate. Today we will discuss the calculation of liquid flow rate. That means we will discuss liquid hydraulics. Liquid hydraulics. The liquid hydraulics is calculated by the use of well known Francis-Weir equation. Francis-Weir equation. Liquid flow rate is calculated by the use of well known Francis-Weir equation. So, for the example distillation column, we will consider the simplified form of this Francis-Weir equation, and that is the linearized form. So, we will consider the linearized form of Francis-Weir equation. So, if Ln is the flow rate of a liquid leaving nth stage, then the Francis-Weir equation correlates Ln equals to Ln naught plus Mn minus Mn naught divided by beta. This is the Francis-Weir form, where Ln is the flow rate of a liquid stream, flow rate of a liquid stream leaving nth stage. Fine. Ln naught is the reference value of Ln. Ln naught is the reference value of Ln. Similarly, Mn is the reference value of Mn naught is the reference value of Mn. Mn naught is the reference value of Mn. Another term is included in the Francis-Weir formula, that is beta. Beta is hydraulic time constant. Hydraulic time constant. The value of beta is typically taken in between 3 to 6 minutes. This beta is taken in between 3 to 6, not minutes, seconds, for each tray. Fine. So, beta is the hydraulic constant, it is typically 3 to 6 seconds for each tray. That means, you see the difference between Mn and Mn naught, that is divided by the hydraulic time constant, then that amount is included with Ln naught to calculate the Ln. This is the simplified version of Francis-Weir formula. Other forms include the nonlinear versions basically. Fine. So, we will consider this simplified form in the example distillation column modeling. Now, this is all about the distillation model. So, the model includes basically the mass balance, total mass balance, component mass balance, then the vapor flow rates which are identical for all trays, equilibrium relationship to calculate the vapor phase composition, and last one is the tray hydraulics for the calculation of liquid flow rates. Fine. Now, we will use this model to analyze the degrees of freedom. Fine. So, next topic is the degrees of freedom for the example distillation. Degrees of freedom Now, here we will consider one example, although we have considered for the previous in the development of the distillation model, that is N. N is basically the total number of trays excluding condenser and reboiler. Fine. We will use this nomenclature, we will use this notation in the degrees of freedom analysis. So, you can recall the degrees of freedom represented by F, which is correlated with V and E by this form. F is the degrees of freedom, V is the number of independent process variables and E is the number of independent equations. So, to calculate the degrees of freedom, we need to find both V and E for the example distillation column. So, first we will go for the number of equations calculations, number of equations and the origin of those equations. We will first discuss this part. So, first one is the equilibrium relationship. Equilibrium relationship. What is the equilibrium relationship we have considered for the example column? That is yi equals to alpha ij xi divided by 1 plus alpha ij minus 1 into xi. Fine. So, how many y we need to calculate? How many y are involved in the distillation model? y1, y2, yn, another y is involved, that is yb. The composition of boiled up vapor. Fine. So, what is the number? N plus 1. Fine. So, total number of equilibrium equations involved in the distillation model is N plus 1. Next is hydraulic relationship. Hydraulic relationship, that is Ln naught equals to Ln equals to Ln naught plus Mn minus Mn naught divided by beta. How many liquid flow rates are involved in the distillation model? L1, L2 up to Ln. N number of liquid flow rates we have to calculate using this Francis-Ware formula. We cannot consider the distillate flow rate and bottom flow rate, although those are liquid flow rates, because those are not calculated by the employment of this Francis-Ware equation. Fine. So, total number of equations N. Fine. Next is component and total mass balance equations. Total and component mass balance equation. How many component and total mass balance equations are involved? First, we will consider for n number of trays. For n number of trays, how many equations are there? 2n. One total mass balance equation, one component mass balance equation for each tray. That means 2 equations for each tray. So, for n number of equations, n number of stages, we have 2n equations. Next, we will consider for the reflux drum. Reflux drum. Number of equations 2. Similarly, for the column base, number of equations 2. One component and another one total mass balance equations. So, total number of equations how many? Total number of equations E, that is equals to 4n plus 5. Total number of equations E equal to 4n plus 5. So, next we have to find the total number of variables V. Next we will calculate number of variables and type of variables, number of variables and type of variables. So, first we will consider the liquid composition. Liquid composition. How many liquid compositions are involved? X1, X2, Xn, one for top section and one for bottom section. Fine. N number of liquid compositions for n trays, one for reflux drum and one for column base. So, n plus 2. Next, vapor composition. How many vapor compositions are involved? Y1, Y2, Yn and one for column base. There is no vapor distillate, we have considered only the liquid distillate. Fine. So, there is no Yd. Accordingly, if we have total n plus 1 equations, n plus 1 variables, those are vapor compositions. Next one is liquid hold-ups. Liquid hold-ups, one for each tray, that means M1, M2 up to Mn, one for reflux drum and one for column base. So, n number of hold ups for n trays and 2 for reflux drum and column base. Fine. So, total number is n plus 2. Next one is liquid flow rates. Liquid flow rates. How many liquid flow rates are involved? L1, L2, Ln. Fine, we are not including the flow rates of top and bottom products. We will consider those separately. So, total number of liquid flow rates N. Fine. Now, apart from these variables, what are the other variables involved in the distillation modeling? First, you will consider the feed. What are the variables used for feed? F and Z. What about top? I mean top section. In the top section, we have another two variables. One is D, another one is reflux flow rate. Fine. And what about the bottom section? One is bottom flow rate, another one is boil off. So, these two are representing the feed, these two in the top section and these two we are considering for the bottom section. So, how many? Then 6. 6. So, V equal to how much? 4n plus 11. We got E equal to 4n plus 5 and we have just calculated V equal to 4n plus 11. So, degrees of freedom F equal to 4n plus 11 minus 4n plus 5, that is 6. Fine. That means this is under specified process. Since V is greater than E, so this is under specified process. We need to make it exactly specified. So, what we need to do? We have to get f equal to 0. How we can get that? There are two ways we have discussed earlier. One is we need to specify more number of disturbance variables. To reduce f to 0, we can specify more number of disturbance variables. So, what are the disturbance variables involved in this distillation process? One is F, another one is Z. F is feed flow rate and Z is feed composition. We can measure this feed flow rate using a flow meter. Then we have the feed flow rate information. We can measure this feed composition by any chromatographic analyzer. Then we have the composition information. If that is the case, then F reduces to 4. Previously F was 6. We are trying to specify these two disturbance variables, that means minus 2. So, F becomes 4. What is the another option to make the process exactly specified? We can incorporate more number of control equations. So, second option is we can incorporate more number of controller equations. So, before writing the controller equations, we need to couple controlled variable, manipulated variable pairs. What are the controlled variable and manipulated variable pairs to be considered for the example column? That we need to decide. So, controlled variable, manipulated variable. See, this is a distillation example. Feed is introduced on a particular tray. We are getting two products. One is the top product, another one is the bottom product. So, what is the control objective for this process? Control objective is to maintain the product compositions, product purity. Fine. That means we can consider one control variable as top product purity, which is represented by top product composition. Another controlled variable we can consider, that is the bottom product composition, XB. Fine. Now, what will be the manipulated variable? For XD, we can consider the manipulated variable, that is reflux flow rate. And for the bottom purity, we can consider the manipulated variable as vapor boil up rate. Fine. These are the standard controlled variable, manipulated variable pairs. Along with these two pairs, we can include another two controlled variable, manipulated variable pair, one for top section and one for bottom section. You see, the reflux drum hold up is represented by MD. Basically, in the reflux drum some liquid is accumulated, and that we represent by MD. So, we can control that liquid height, and that liquid height we can control by the adjustment of distillate flow rate. Some liquid is accumulated after condensation in the reflux drum. So, there is a scope to maintain the liquid hold up, or we can say there is a need to maintain the liquid hold up in the reflux term. So, if that is our objective, we can consider MD as the control variable, and that can be adjusted by the outlet flow rate D. By the similar fashion, we can consider the hold up in the column base MB as the another control variable. Some liquid is accumulated in the column base, which is represented by MB. If that is our objective, I mean if we want to maintain the liquid hold up in the column base, then that is the control variable, and this MB can be manipulated, this MB can be controlled by the manipulation of outlet liquid flow rate, that is B. So, these 4 control variable manipulated variable pairs we can consider for the example column. So, one manipulated variable is R, and the controller equation, although we did not discuss that part, we will discuss later. I am just adding, I am just writing the equations, controller equations. If R is the manipulated variable, then one controller equation is RS plus KCR XD SP minus XD. Previously we have used suffix D for the desired value. Here we are using SP. SP is the set point. Fine. SP means, SP denotes set point. Set point is nothing but the desired value. Fine. And this RS is the steady state value of R. In process control, we call RS as bias signal. RS is the bias signal, that is basically the steady state value of reflux rate R. KCR is the controller parameter which we need to determine, or we call tuning parameter, that is basically a constant term. XD SP is the XD set point, that means that is the desired value of XD, and this is the actual XD. So, this is one equation. Similarly, we can write for D, DS plus KCD, MD set point minus MD. Fine. For VB, we can write VB equals to VBS plus KCV XB set point minus XB, and last equation is B equals to BS plus KCB MB set point minus MB. These are the control equations, total 4 equations. So, if we include 4 equations, then degrees of freedom becomes 0. Previously, we had degrees of freedom equal to 4. After defining 4 control equations, our degrees of freedom becomes 0. Fine. Now, we will discuss how we can select the manipulated variable control variable pair for the example system. How we have selected these 4 control variable manipulated variable pairs, that we will discuss in brief. This is the distillation tower, feed flow rate with composition. One condenser is installed at the top. This is the reflux drum. Liquid is accumulated here. The hold up is MD. This is the top stage. Suppose this is a control valve which is used to manipulate the reflux rate. This is another control valve which is used to manipulate distillate flow rate. This is reflux flow rate. Fine. At the bottom section, this is a bottom tray, this is feed tray, some amount of liquid is accumulated here. Now, this is the reboiler. This is one control valve which is used to manipulate vapor boil up rate. Another outlet section is included for the outflow of bottom flow rate. Fine. Now, we will consider first the top section, I mean this section. This is the top section. In this top section, you see we have selected two control variable based of our control objective. One control variable is xd, another control variable is md. These two we have selected based on our control objective. So, how many equations are available for manipulation in the top section? Two variables are available for manipulation. What are those variables? One is R, another one is D. These two variables are available for manipulation. Now, we have to pair the control variable and manipulated variable. We can pair xd, d and mdr, fine. Another pair may be xd r and md d. So, these are two possible pairs. First, we will consider the first pair. We want to manipulate, suppose md, we want to control md by the manipulation of r. There is no problem, we can do that. If we consider the control of md by the manipulation of r, we can easily do that, there is no problem, because this is also outflow, I mean this is also outlet flow, this is also outlet. So, we can choose any one for controlling the md. Another option is xd versus d. Suppose we have the distillate composition at the present time 95 mole percent, I mean the distillate purity presently is 95 mole percent. Now, we want to change it to 98 mole percent purity. We want to change it to 98 mole percent purity. It is perhaps not possible to get 98 mole percent purity by the manipulation of distillate, fine, but it may be possible to get 98 mole percent purity by the manipulation of reflux flow rate, because if we want to get 98 mole percent purity, there is a need to increase the reflux flow rate, which will affect the separation in the process, and there may be some improvement of composition in the top section, fine. If we want to increase xd, there is a need to increase reflux flow rate. That will affect the separation in the process, and then there may be some improvement in composition. It is usual for the binary distillation column. If we want to increase XD, there is a need to increase reflux flow rate, because we are not allowing to leave the process. We are again treating that steam in the process so that there is some improvement can be achieved. Fine. So, XD versus D is not a good option, and the second option gets preference. I mean XD versus R, and this is not MB, this is MD. MD versus D, this is the best option among these two. By the similar way, for the bottom section is this one. This one is the bottom section. By the similar way, for the bottom section, we choose XB versus VB and MB versus B. You see, MB can affect the process, fine, but B is leaving the process. So, by the similar way, as we discussed for the top section, this is the best option for the bottom section, XB versus VB and MB versus B. Fine, this is all about the mathematical modeling, degrees of freedom analysis of a distillation column. Next we will start, we will just try to know in brief the Laplace transforms. I hope you have started this in your basic mathematics course. So, we will not discuss this in details, but we will just recall the Laplace transform by some standard formulas. So, next we will start the Laplace transform, and in brief we will know the standard formulas. Basic equation of the Laplace transform of a function f t. The Laplace transform of a function f t we represent by this. F is a function and t is the time independent variable. This is equal to f bar s, the function which is written in Laplace domain, equal to 0 to infinity function of t e to the power minus st dt. This is a standard formula. Now, we will just write the formula in terms of time function, where time t is greater than or equals to 0, and the Laplace transform of those functions. Fine. If this function equal to 1, the Laplace transform is 1 by s. Function equal to t, 1 by s square. If this is equal to t square, factorial 2 by s cube. Fine. If this function is t to the power n, then this becomes factorial n divided by s to the power n plus 1. If this is e to the power minus at, Laplace transform of this 1 by s plus a. This is t to the power n e to the power minus at. Laplace transform is factorial n divided by s plus a whole to the power n plus 1. If this is sin omega t, omega divided by a square plus omega square. Then this is equals to, suppose, cos omega t, s divided by a square plus omega square. This is sin hyperbolic omega t. Laplace transform is omega divided by a square minus omega square. If this is cos hyperbolic omega t, Laplace transform is s divided by a square minus omega square. Next one is exponential of minus at sin omega t. Laplace transform is omega divided by s plus a whole square plus omega square, and e to the power minus at cos omega t, it has s plus a divided by s plus a whole square plus omega square. There are other functions also defined in different textbooks. I mean, Laplace transform of different other functions, more functions are available in textbook. So, we will not discuss the Laplace transform with any more functions. So, next we will just consider the Laplace transform of derivatives. Laplace transform of derivatives. Fine. For the first order equation, Laplace transform of dft dt equal to s f bar s minus f naught. Fine. This is for first order differential equation. Similarly, if we consider second order equation d2 ft dt square, we get s square f bar s minus s f naught minus first derivative of f naught. This is for the second order equation. Similarly, for nth order equation ft dtn equal to s to the power n f bar s minus s to the power n minus 1 f naught minus s to the power n minus 2 first derivative. By this way, last term will be n minus 1th derivative. at 0. Fine. Now, if we consider f as the deviation variable, suppose f is a deviation variable. Deviation variable means if at any time t the value of f at any time t minus the value of f at steady state. Then we can call this variable f, here it is function, as a deviation variable. Fine. That means, if we consider this is a function, so it is a function of deviation variables. If we consider f as a function, f as a deviation function, that means it is the function of deviation variables. Now, the definition of deviation variable is this: the variable at any time t minus the value of variable at steady state. If that is the case, I mean if we consider f as the function of deviation variables, what will be this first derivative? I mean the Laplace transform of first derivative. This will become 0, isn't it? That means in this t equals to 0. So, f at t equals to 0 minus f at steady state. We usually consider time t equals to 0 is the steady state. So, this becomes 0. Similarly, these two terms become 0. Similarly, all these terms equal to 0. Fine. It is the usual practice in process control. The variables in the model are considered in the form of deviation variable. What is the Laplace transform of integrals? Laplace transform of integrals. Laplace transform of a integral of function of t dt equal to 1 by s f bar s. If we consider f t as a function in time domain, then the integration of that function is this one, and Laplace transform of that function is this 1 by s f bar s. Other two formulas are also in use in process control. Those are final value theorem and initial value theorem. Final value theorem. Fine. Final value theorem is limit t tends to infinity, function of t equal to limit s tends to 0, s f bar s. This is the final value theorem. If our modeling equations are in time domain, then we have to consider this. If our modeling equations are converted to Laplace domain, in that case we have to consider this. Fine. Another one is initial value theorem. Initial value theorem is limit t tends to 0, ft equals to limit s tends to infinity s f bar s. This is the initial value theorem. Similarly, if the modeling equations are in time domain, we have to consider this. If they are in Laplace domain, we can consider the right hand formula. So, these are about the in brief about the Laplace transforms. Fine. Next we will go to discuss the different forcing functions. Forcing functions are usually the input variables. I mean, suppose we have a process, this is a chemical process. This is the input to the process and this is the output. Fine. Now, suppose initially the process is at steady state. Initially the process is at steady state. We want to investigate the transient behavior of this process. We want to observe the dynamics of this process. How we can observe that? By the use of simulator. We have to introduce some change in input variable. If we give some change in input variable, then we will get some change in output variable. That is basically the transient behavior of a process or the dynamic characteristics of a process. Fine. So, what type of input variables we will consider in our process control course, so that corresponding output behavior we can observe from the simulator, that we will discuss next. Now, there are different input variables which we will consider. Those are like step input. Fine. Another one is pulse input. It is better to write step input function, pulse input function, then ramp input function, fine. So, these functions are basically called forcing function. I mean, we will use this name, forcing function. Now, we will give change in input variable, say by this fashion, we will give change in input variable as a step input. Then we will observe the output dynamics. Similarly, we can consider the pulse change in input variable, then the effect in terms of output variable, change of input variable as ramp input, I mean ramp change, then the transient behavior in terms of output variable. That we will discuss in the next class. Fine, thank you.